Hi, and welcome to lecture 13. In this lecture, we will conclude our discussion of the dual optimization problem for the support vector regression, and we'll also discuss how the dual leads to some very interesting representation through an implicit feature space and allows for efficient computation of the kernel. So recap the KKT conditions where we had an expression for W, the weight vector, which was purely in terms of a linear combination of the Lagrange multipliers alpha i's and the feature vectors phi xi. We also found some conditions, linear equations involving alpha i's and mu i's, alpha I stars and mu I stars, which led to an observation that if alpha I was restricted between 0 and c, open interval, this would basically imply that mu I is also in that open interval by virtue of the sum alpha I plus mu I equals c. On the other hand, this would also imply that a non-zero value of alpha I would mean equality for yi minus w transpose phi xi minus b minus epsilon minus xi. So this basically means that yi minus a function at xi minus epsilon minus xi would be 0. Now mu I between 0 and c would imply from the complementary slackness that xi is equal to 0. So substituting for xi equal to 0, what we get is all these points alpha I between 0 and c are the points where yi basically equals f of xi plus epsilon. That is, these are points on margin. Similarly, you can argue for alpha I stars or points with alpha I star that lies strictly in the open interval 0 and c. You already discussed that for SVR with convexity conditions, the KKT conditions give optimality as sufficient conditions as well. So what we are talking about is optimal solutions. And summarizing our discussion from before, all points with alpha between 0 and c are points like that on the boundary of the epsilon band, and using any such point xj on margin, we can recover the b. So the b is nothing but yj minus w transpose phi xj minus epsilon for any point, any single point or a specific index j with alpha j between 0 and c. Now we move on to the dual objective. We will revisit these conditions in the context of the dual. So invoking the weak duality result, we know that the dual optimization Lagrangian is basically the min over the primal variables of the Lagrange function. From the weak duality theorem, we know that the original primal objective is greater than equal to the L star, which is the minimum of the penalized objective through the Lagrange function. Of course, this penalty should be such that alpha and alpha star are all greater than equal to 0. So what does this mean? Well, this means that you could also take an upper bound of the right hand side. What have we done here? We have said taking a max of the lower bound bound on the lower bound. Why are we allowed to do that? Because the upper bound is computed with respect to the dual variables, which don't figure on the left hand side at all. So what have we done here? We basically saying that if f of y is greater than equal to g of x for all x, then this should mean that f of y is greater than equal to the max over x of g of x. That's all we're stating here. Now some questions. Is this inequality an equality? When will it be an equality? And we've already seen that for support vector regression, by virtue of convexity conditions, you should have equality here. But equality where? So how do you make use of this equality? So we will invoke the KKT conditions and consider the dual optimization problem projected onto the KKT plane or KKT subset, so to speak. So the dual objective is equal to the primal by virtue of convex objective and linear constraint. We have sufficiency here. Needless to say, we are still looking at alpha i's that are positive and alpha I star that are positive on the right hand side. Now we don't have to explicitly consider these positivity constraints, etc., if we understand that we could restrict the primal and the dual variables along the KKT condition set. So let's call this the KKT constraint set. So what is KKT constraint set? Is basically all the W's, the B's, the X's, the Xi stars, the alpha star, the mu and the mu star that satisfy KKT conditions. So what we are going to do is we're going to solve the dual optimization problem as an equivalent alternative to the primal, but we will simplify by restricting this optimization problem to the KKT set. So we'll formulate an equivalent, simpler optimization problem restricted to the KKT set. So what we do here is we invoke the KKT conditions derived earlier. We know that at the point of optimality you would ideally put a hat, a W hat is expressed in terms of the alpha I hats and the alpha I star hats. There are additional constraints involving the alpha I stars, alpha i's, of course the hats on. In subsequent slides we will be dropping the hats. So when we make these substitutions, what do we get? As an example, if you factor out all the terms that involve the B, so let's consider B times alpha I, that's a summation, a minus of alpha I, and there is a plus of alpha I star. You would expect, so L would have a term involving the B with a summation over the alpha I star and the alpha i's. This of course at the point of optimality. We're going to project along the KKT conditions. We'll drop the hats because we are considering the KKT plane and not necessarily a single value. So we look at these KKT set, constraint set, we find that this summation is actually 0. So the term involving B should vanish. Similarly, we can argue for some other terms. Look at the terms involving Xi i's. What would we get? We would basically get an expression that is xi I times or summation xi I times mu I I guess there's a minus missing here, so you'll have minus of mu I minus of alpha I. There's also an additional term involving C. Okay, so this is xi I times minus of mu I minus alpha I plus C. But what we know that alpha I plus mu I equals C along the KKT set. So again, the terms involving xi i's should vanish, the terms involving xi I star should vanish. We'll also substitute for w hat w along the KKT plane into the Lagrange expression, and what do we get? We'll get terms, quadratic terms involving the dot product of phi's for xi's and xj. So let's write it down. This is what we would get. We would rearrange to find the dot product terms. There will be these dot product terms involving phi xi transpose phi xj, one with a half component and the other with a minus. So these two would actually simplify to give minus 1/2 summation over I summation over j alpha I minus alpha I star alpha j minus alpha j star phi xi dot product with phi xj. Additionally, as pointed out earlier, the terms involving xi i's would vanish because alpha I plus mu I equals C, and what we have here is C minus alpha I minus mu I. This whole thing should just vanish. Similarly, the terms involving xi I star should vanish. The term involving B has a summation alpha I minus alpha I star, that should vanish. So what we'll be left with are the terms involving epsilon, yi's and the dot products. So we would have the sum of the alpha i's and alpha I stars with epsilon plus a term involving yi with alpha I minus alpha I star. Note that this doesn't vanish because there is a multiplication with yi for every alpha I minus alpha I star. So here's our final objective simplified, and as I mentioned, we have basically projected along the KKT set. So you must note that the decision function could also be rewritten based on w's projected along the KKT set, and this decision function will again start involving the dot product of phi xi's with the phi x. The x is a query point, and we have also substituted for b. Recall that b could be obtained as yj minus summation minus epsilon. Now the summation again turns out to be a dot product. So this is of course for a specific value of j, alpha j between 0 and c. So what we find is fx is also involving only dot products, dot product of phi xi with phi xj. The only way you view the data points is through the dot product. You can recall the similarity we have seen with ridge regression, where we were able to express the decision function fx as summation over alpha I kxi xj kxi x, basically summation over alpha I, the dot product of basis function at xi with the basis function at x. So we have already seen this, the kernelized expression for ridge regression. However, there we found a closed form solution for the alpha i's. Here we have to do iteratively computation for the alpha i's. We'll see this soon. So let's write down this dual optimization problem. We know that everything now can be written in terms of the dot product of phi's. So dual optimization problem projected along the KKT plane. So I must mention that this is projected along or projected on KKT set, and you will of course need to also include constraints from the KKT set. Everything is in terms of dot product. So dot product for the decision function, for the B involved in the decision function, the objective has a dot product, and there's no other way that you view the data points other than this dot product. So the idea is to call this dot product by some kernel function. This is basically a kernel function. Why are we interested in doing this? Well, potentially we could have these phi's embedded in some very large dimensional space, and we'll see an example of that very soon. Phi's could come from some very arbitrary polynomial function, but the dot product could be computed very efficiently without necessarily having to enumerate the phi. So you can recap that we had something very similar from ridge regression. When we kernelized ridge regression, we had the decision function purely in terms of the dot products. Of course, we had a closed form expression for all phi's. This privilege we won't enjoy for support vector regression. So we'll need to compute the alphas iteratively in the case of support vector regression. So the kernel trick is basically that for some important choices of phi, compute this kernel function directly and more efficiently than having to explicitly compute or enumerate the basis functions, basis vectors. So as I already pointed out, the closed form for alpha I exists for ridge regression but not for support vector regression. So now we write the whole formulation in terms of the kernel function k, and as I said, the computation of kernel could often avoid computation of the phi's or enumeration of phi's explicitly. So this is the basis function expansion in the original space weighted linear combination of the basis functions, now being replaced with a slightly different form of basis function expansion, a weighted linear combination, but the basis functions are in some sense provided or indexed by examples. Phi I of x comes as kx comma xi. Question is, the general question is, for what kind of regularizers, loss functions will these dual representations hold? For example, if you consider the penalized regression model, min of phi w minus y norm square plus lambda times some p norm of w. Question is, for what kind of P will these dual representations hold? Will this hold for P equals 1? So it isn't necessary that you can recover this dual form in terms of kernel for all choices of P. Let's take an example kernel. So consider this kernel which involves a dot product between xi's is 1 plus x1 transpose x to the whole square. Now does this correspond to a dot product of some phi x1 with phi x2. Is such a phi guaranteed to exist for any arbitrary choice of k that I come up with? And is such a choice unique? We'll attempt to answer at least the first question now. We can assume for the time being that these points x1 and x2 are in 2 dimensions. The extension to multiple dimensions is very straightforward, as we will see subsequently. So consider x1 and x2 in R2. What expansion could give you the desired kernel? So obviously we might need more than 2 entries. What would be the first entry be like? Would it be some eta 1 times x11, eta 2 times x11 square, eta 3 times x11 x12, eta 4 times x12 12 square, and of course the other term, which is eta 5 times x12. Would some choice of the etas give you the kernel that is desired? So it turns out that it is the case. Actually, you need to also pad a 1 here. You need a constant. So yeah, the etas are, some of these etas are just root 2 and some of these etas is 1. So there does exist such a phi xi in a phi. Actually, it's a 6-dimensional space. 6-dimensional space actually, discounting the 1. But what we notice is, to compute this kernel, all we need is the dot product of the xi xj. So this dot product is basically a very simple computation which involves 2 multiplications and 2 additions. However, if you were to compute the same thing in this space, you would need all these multiplications for each of the phi xi's. You would we already need 3 multiplications basically. The square is also multiplication, and then the dot product. Of course, what we also need for computing the kernel is 1 plus x1 transpose x2 raised to 2. For the simple 2-dimensional case, the gain may not be much, but for very large dimensions, this simple square is just a square of a scalar, one single scalar, whereas you would really avoid enumerating a extremely large phi. So you can easily see that the kernel trick helps computationally. And does it help empirically? Well, it turns out that there are kernels such as the RBF kernel, where k of x1 x2 is an exponentiated distance now this exponentiated distance can be computed as dot product of phi's, but in an infinite dimensional space. Now you can see from this curve that the RBF model, the choice of the RBF kernel in the SVR model, gives you much better fit, at least on the training set. A lot more points get satisfied. You were able to find very non-linear fits. The polynomial model has a finite dimensional representation, which is nothing but 1 plus x1 transpose x2 raised to some power d. It isn't too bad, or at least much better than the linear fit. The linear model is our standard x1 transpose x2. So the kernels operate in high dimensional implicit feature space, where the implicit feature space phi can be avoided in terms of being enumerated. You just simply compute the kernel function. This can be done for an entire data set. So let's consider a data set D, which consists of points x1 to xm, and let's say we consider computation of the kernel function for every pair of points. What you then get is something called the gram matrix. The gram matrix is the matrix of computations of kernel. So this K has an ijth entry, the dot product of phi for xi and xj. We will build some intuition for what is a valid kernel by making some observations on this matrix. So we observe that this gram matrix must be positive definite. Why? Well, all you need to do is convince yourself by writing down the quadratic expansion B transpose KB is nothing but summation over all ij bi kij bi bj. Kij is nothing but phi xi dot product with phi xj. Now the bi's and the bj's could be taken inside the dot product to the respective phi xi and phi xj respectively. In fact, you could do the following: you not only move the bi's and the bj's, but you also move the summation inside, because the sum of dot product is kind of the dot product of the sum when you are summing over two indices I and j. So I and j basically get distributed, and what you have is a dot product of two linear combinations of vectors over all the points. Now what are i's and j's? Basically they are indices on the same set, indices on same data set D. So therefore they must be the same, and the dot product of the same of a vector with itself is nothing but its Euclidean norm square, and we know that this norm should be greater than or equal to 0. So thus any gram matrix must be positive semi-definite. So we'll consider the positive definite kernel as a kernel function such that for every subset of points or m points here, the gram matrix that you compute will turn out to be positive definite. One can always recover the phi corresponding to such a matrix by doing eigenvalue decomposition. The eigenvalue decomposition on the positive definite K would give you a sigma of eigenvalues which are all positive. So therefore I could alternately represent this K in terms of the product of a matrix with its transpose, where the matrix has linearly independent rows. So basically what we have done is an orthonormal decomposition of the gram matrix to give you the phi. So you can actually write this each of this R can be thought of as phi applied to every data point, phi applied to x1, phi applied to x2, and so on. You can convince yourself that R transpose is nothing but the matrix of phi transpose. We are interested in extending this intuition to an arbitrary function. So please note that computing the kernel matrix isn't really practical for an arbitrary choice of the kernel function. You don't want to do positive definite test for every possible kernel matrix, but what you have is a trick based on something called the Merzel kernel. This is about extending the eigenfunction decomposition, extending the eigenvalue decomposition to function decomposition. And a Mercer kernel is one where you're able to write the kernel as a product of basis functions phi j applied to two different points x1 and x2 with a positive scalar alpha j. All you need is that the alpha j squares are less than infinity. Now you can also include the alpha j's into the phi j's by taking the square root. Now it turns out that the Mercer kernel and positive definite kernel are equivalent if the input space X is compact. A compact space is where every Cauchy sequence is convergent, which means sequences that come arbitrarily close to each other in the Cauchy sense are convergent. How is this going to be useful? There's something called the Mercer theorem. The Mercer theorem says that for any Mercer kernel you have a dot product decomposition. There exists a phi going from the input space x Rn to some Hilbert space, which is an infinite dimensional version of the Euclidean space. Suffices to live with that intuition for the time being as far as Hilbert space are concerned. So one can easily see the underpinnings of the Mercer kernel with a positive definite kernel where we showed eigenvalue decomposition. So we were able to recover a phi through the R matrix. It turns out that you can do the same thing for any Mercer kernel. How is this useful? So the Mercer kernel is defined as, well, it equivalently defined as one where this integral, this quadratic expansion, quadratic but integral based expansion, this is the analog of V transpose KV, but now the V has been replaced by a function. All you need is that, just like the V, the square of the integral of the square of G should be finite. So what we need is this positivity of this quadratic expansion for all square integrable functions G, which is a generalization of the vector V. So the Mercer kernel will give you a phi implicitly. That's a guarantee we want to exploit. Can we do that? Let's consider an example. So let's say we want to prove that x1 transpose x2 raised to d is a Mercer kernel. So let's say we make the substitution x1 transpose x2 raised to d and actually verify that this quadratic expansion is indeed always positive for all square integrable functions G. So expanding and realizing that x1 transpose x2 is nothing but a sum over x1i, x2i, the sum of the products of the individual components. If one does the expansion, we'll realize that this raised to d would involve coefficients for terms that involve x1i and x2i raised to some ni. So there would be a product over the ni's, product over the i's for different values of ni's. But this can happen for as many configurations as the number of ways you can choose these ni's from D. What would that mean? It will basically mean d factorial divided by n1 factorial, n2 factorial, ni factorial, nt factorial. So this is precisely what we have written here, and we have a summation sitting outside, sum over all values of n120 for every possible configuration. Of course, the constraint is that the ni should sum to d. How do you simplify this? Well, we realize that some of these integrals could be pushed into the summation. We also realize that the summation itself could be written as a product. So let's do that one at a time. So what we have done is push the integrals into the summation. Basically, think of these integrals also as summations, but over infinite number of terms. We still have the product inside. We try to simplify the product by writing this as a product of two different terms. One's involving only x1, the other involving only x2. This is a function of x1, this is a function of x2. So note that all this is for a fixed configuration of the NIs. What next? Well, we realize that the h of x1 and the h of x2 are kind of independent of each other, so you could simplify and perhaps write this as integral over x1 h of x1 integral over x2 h of x2. Why? Because it's basically sum of product that you are able to write as product of sum because of this independence of h between x1 and x2. That's what we have written here. The integral of h of x1 into the integral of h of x2. What do we realize? Well, we realize that ultimately you're integrating over all x1 and or x2. So these two terms are the same. What you basically have is summation over some factor of the square of an integral h of x1 dx1 square. This is basically guaranteed to be non-negative. Of course, we have made an assumption that G is square integrable. Thus, we have shown that x1 transpose x2 raised to d is a Mercer kernel for any integral value of d. Can we take this further? We could also show that linear combination of the dot products raised to d is also a kernel, and this is very simple because all we have is integral over sum, which can again be written as sum of integrals. This can be rearranged by bringing the integrals, and what do we see? Well, this was guaranteed to be positive or non-negative, so entire sum should be positive or non-negative because we know that the alpha d's are non-negative. So we have shown that the summation is a Mercer kernel. So a polynomial kernel is basically the Mercer kernel. What is a polynomial kernel? It is 1 plus x1 transpose x2 raised to d, and this is nothing but summation over alpha d, summation over d of alpha d x1 transpose x2 raised to d, which is for some specific choice of alpha d's. So you can show that the polynomial kernel is an example. The radial basis kernel function is the same but over an infinite number of alpha d's, so that you can show that e raised to by 2 sigma square norm of xi minus xj square is also some kind of a linear, positive linear combination, but this is what an infinite number of alpha d's. This possibly has also some other factors. So here's a summary. We have this dual optimization problem and a decision function all in terms of the kernel. One can now employ any Mercer kernel in SVR or ridge regression to implicitly perform linear regression in higher dimensional spaces. The challenge, of course, is computing alpha i's. For ridge regression, the alpha i's have a closed form expression, assuming that the phi's can be enumerated. However, for support vector regression, you could compute alpha i's iteratively by invoking something called projected block coordinate ascent. What is this basically? Well, we can ignore block for the timing, but coordinate ascent is a form of steepest ascent where you choose a subset of variables to optimize on at every iteration, and in every iteration as you progress, say along alpha 1 and alpha 2, you find alpha new, alpha 1 new, alpha 2 new in terms of the alpha 1 old and alpha 2 old. You also make sure that you project the modified the modified updates along the constraint. Project modified updates along the constraints. For example, what are the constraints? We have summation alpha I minus alpha I star equals 0. We also know that alpha i's and alpha I stars should all be positive. It turns out that they're very efficient algorithms that achieve this. In particular, there's one very useful algorithm called the SMO algorithm. More about this later. So going back, the impact of such iterative fits is that in implicit high dimensional feature space involving the RBF kernels or polynomial models, very efficiently we are able to compute these fits. We can also make use of concepts of optimizations learned so far to find equivalent forms of ridge regression. So recall that we had one version of ridge regression where we put a constraint on the norm of W, and we wanted to find a transformation from this to the penalized version where there's a penalty on this norm right within the objective. So let's try and see how they have some correspondence. So you find that the constraint function g of W, which is norm W square minus xi less than equal to 0, this constraint is also convex. The set is convex thereafter. The objective function is strictly convex, so we could actually make use of the KKT conditions as necessary and sufficient conditions. That's what we do next. So we apply the KKT condition. The first thing is consider the Lagrange function and the gradient of the Lagrange function in terms of W and lambda. Now what is this Lagrange function? Well, L of W comma lambda is nothing but phi W minus y norm square plus lambda times norm w square minus xi. So when you consider the gradient of the Lagrange function with the FWs and the GWs and solve, as we've done before, for the penalized ridge regression, we'll actually find this expression W star is phi transpose phi plus lambda I inverse phi transpose y. This lambda now corresponds to the Lagrange multiplier. From the second KKT condition, we still need the norm of W square to be restricted or upper bounded by xi. The lambda should of course be positive. And we also have complementary slackness conditions. Lambda times the norm square is equal to lambda times xi. That is, either lambda is 0 and the inequality is satisfied, maybe strictly, or you have an equality here and lambda need not be 0. So well, such lambda, will that exist? Well, here is a simple argument. Suppose with lambda equal to 0, you get W star as phi transpose phi inverse phi transpose y, and you compute its norm, well, norm square, and find that it's actually less than equal to xi. So then you already have a solution, which means the ridge penalty lambda turned out to be 0 for the specific choice of xi. So of course, if you increase xi, decrease xi, then this would make lambda not equal to 0 inevitable. So as you shrink the value of xi, lambda will be forced to be non-zero. Why? Well, as you actually add a lambda I component to phi transpose phi, we already seen that the eigenvalues for this matrix phi transpose phi plus lambda I will definitely increase. This leads to a reduction in the overall norm, because we are ultimately looking at the inverse of this positive definite matrix. So this can be shown that as lambda increases, the norm of W square, we miss a square here, shrinks. And therefore, for some specific value of lambda, you're able to actually meet the inequality constraint with respect to xi. We can do a little bit more, and we can actually write down some possible bounds for lambda. So consider the solution to the KKT condition. We basically multiply phi transpose phi plus lambda I on both sides, and we get this very interesting norm equation. We bring phi transpose y to one side and lambda phi transpose phi plus lambda I to the other side. That's what we have done. And then we also take the norms to get this inequality. On this norm, we invoke the triangle inequality. So phi transpose phi W star plus lambda W star, a norm of W star should be greater than equal to the norm of the sum. The sum of the norms is greater than equal to the norm of the sum. Next, we also invoke the Cauchy-Schwarz inequality. Phi transpose phi W star is less than equal to alpha W star, where alpha is the norm of phi transpose phi. So if you substitute this, basically you get alpha plus lambda times norm W star should be greater than equal to the original right hand side phi transpose y. What does this tell us? Well, it says that lambda is lower bounded by phi transpose y divided by norm W star minus alpha. So as lambda tends to infinity, the norm of W star will shrink. So using norm W star square less than equal to xi, we get the desired correspondence between xi and lambda. And the correspondence is that lambda is greater than equal to 1 upon xi phi transpose y minus alpha. Well, actually there will be a root xi because of the norm involvement of norm of phi transpose phi. So this is just an intuition that there exists such a lambda for corresponding xi and phi. Now we can see that by substituting norm w substituting for GW in the first KKT condition, we get a equivalent formulation in terms of this lambda. The lambda was a Lagrange multiplier, but for the same choice of lambda that satisfied the KKT condition, which we showed can be satisfied. You get the penalized version of regularized ridge regression.